Now that we know how convolutional operations work, in this video, we're going to learn about the various advantages of convolutional operations. So let's dive right in.
Advantages of convolutional operations. So we've already seen before that convolutions gives us an advantage in terms of reducing the number of parameters and thereby regularizing a model. Through these parameter sharing that we get by having these local receptive fields, we can have drastically lowered the number of parameters than what we would have had with fully connected layers that would connect directly to each pixel in a given input image. And in general, we can say that convolutions leverage these three important concepts, namely sparse interactions, parameter sharing, and equivariant representations. And let's look at each of these in more detail. First, let's look at sparse interactions. So when we have a feed-forward neural network, then of course we represent a layer by some nodes with its own set of parameters by matrix multiplication here. And we have a separate parameter describing how a given input interacts with each output unit. And in convnets, you only have these local receptive fields. So you have the sparse interaction between each of the inputs with a given convolutional unit. And in this way, to visualize, we can see what is shown here in this slide. So we have one input in this view for the top unit here. So we see the unit X3, and this X3 unit only interacts with S2, S3, and S4 here. So if you think of a fully connected form, then X3 here basically interacts with all S1, S2, S3, S4, and S5. So basically the top one is for a CNN, and the bottom one is for a feed-forward neural network here. So since we only have this filter window that is moving in this direction along the input stream, only these three units will process in a CNN. Here again, you have the CNN unit in the top and the feed-forward unit in the bottom. So let's just write this to avoid confusion. So the CNN now shows you which of these activation layer units interact with how much of the input. So X is the input and S is the activation layer here. So we see that the activation for the activation S3, the receptive field is only X2, X3, and X4, whereas for a feed-forward neural network, we see that the receptive field is much larger. So all the inputs basically react for this one neuron S3 here. And that's basically from X1 to X5 will contribute in the convolution to give the S3 unit here. Okay, so now as we stack these units with sparse interactions in convolutional layers, we can see that although they are restricted initially in the receptive fields, the size of the receptive fields grows as we go deeper and deeper into the layers of the convolutional neural network. So let's see that with this example. For this unit here, H2, it only interacts with X1, X2, and X3 here in the middle layer. So each of them, all these units in the middle layer only interact with 3 units in the input layer here. However, if you go into higher layers, for example, the G3 unit here, you see that it goes through all these units. This means that potentially all the units can collaborate for processing the G3 unit. So it encompasses all the units from X1 through X5. And that is what is visualized here. So there are also some forms of convolutions that we called as dilated convolutions that we will look at in the miscellaneous convolutions lecture later. And these convolutions have skipping alternative units. So what this gives us is basically that we can have a large receptive field, but not increasing the kernel size. So by skipping one convolution and not skipping one unit and not having to interact with all the units, we can use the same kernel size of 3, but we can have a larger receptive field. So we will look at more into detail in these dilated convolutions in the miscellaneous convolutions lecture that will follow. So as I said, we have these local receptive fields that we slide across the input to create the feature maps from the input to the hidden layers, and you use convolutions to implement this. So this substantially brings down the number of parameters that we previously saw. So if you have m inputs and n outputs, then these matrix multiplications require m times m parameters, and these algorithms that we use in practice have O of m times n as the runtime. So this is in the case of a fully connected network, whereas in the case of convolutional neural network, we limit the number of connections in the output to k, where k is the receptive field. Then the sparsely connected approach requires only k times n parameters, and this yields a runtime of O of k times n. And this is in the case of convolutional neural networks. So what we saw before is also closely related to parameter sharing. So not only do we restrict the number of inputs in the receptive field, we also want to reuse the weights for this receptive field for each particular region that we slide the kernel over during the convolutional operations. So in the traditional feed-forward neural network, we would use our weight matrices only once when we compute the output, whereas in ConvNets, each member of the kernel will be used at every position in the input. Maybe this would be easier if we visualize this. So here in this slide on the top, you can see again for a CNN, and on the bottom, you can see for a feed-forward neural network. So the top layer here is the activation map that you can see, and X is the input layer that you can see here. So the dark arrows that come up to each of these calculations, it means that it's the same weight that is being used again and again. So it's the same weight for the input X1 to give activation S1. It's the same weight again for X2 to give activation S2, and so on. So this goes on until X5. Whereas if we see in a feed-forward neural network, only this particular weight contributes to S3. So X3 contributes to S3 contributes to X3, whereas for all the others, they have their own weights. So these weights are not reused in the other scenarios in case of feed-forward neural networks. So as we saw, weights and biases are the same for all hidden neurons in the same layer. And this does not affect the runtime for forward propagation. It's still O of k times n, but it does further significantly reduce the storage requirement of our model in terms of the number of parameters, and the convolutions also reduce the number of dense matrix multiplications. So which in turn then reduces the memory requirements and the efficiency, as well as in terms of the operations that we have to perform. Okay, so next is equivariant representations. Equivariant representations is now a result of applying these convolutions. This means that it does not really matter where these features are located in the input image for a given filter in order to have the maximum output. So if your filter is specialized to find edges, let's say oriented at about 45 degrees, this could be in the top left corner of the image or the bottom right corner of the image, so it doesn't really matter. So as long as you slide this filter, it will have the same output value as it detects at a particular region in the image. So this means that as the input changes, the output also changes in the same way. So for a function f of x to be equivariant to a function g, we can say that f of g of x should be equal to the function g applied to the function f of x. So this is what we mean mathematically by equivariant representations. Okay, let's look at this through another example again. So if we have a function I giving the brightness of an image at each pixel, then you have a function g mapping I to I prime, where the mapping is given as the shift in one pixel in the x direction to the right. Then if you apply convolution to this, the result of the convolution should be the same as before, but also just shifted in the x direction by 1 pixel. And we can also use this to produce time-dependent data, not only in images, but also while doing 1D convolutions, for example. So if you apply 1D convolutions over time, we do the same thing by shifting the input either in 1 times the forward or the backward, or even several time steps. And if we apply convolutions, then the output will also be shifted accordingly. And this is a very useful property to have in convolutions. All right, so this brings us to the end of this video. I have one question for you. So at which stage of a CNN is the receptive field the largest? So is the receptive field the largest in the beginning, in the middle, or in the end, or as we go into deeper layers? So I encourage you to pause this video now and try to answer this question, and we will continue in the next video. Thank you.